you that study psychology, or those of you that talk to people that study psychology, the usual question that you get if you say, I'm studying psychology or I'm a psychologist is, oh, then I have to be careful about what I'm going to say next, because that means you can read my mind. And if you hear that for 1 or 2 or 3 times, it's funny, but after a while it gets a bit boring, right? So what I did back then is I decided, instead of saying I'm studying psychology, I made up that I'm studying veterinary medicine. But what I'm trying to convince you about today is that maybe the better answer would have been, well, actually, yes, I can. And there are some very interesting techniques, and we got quite far. And this is what I want to tell you about today in today's talk. So, in order to tell you a bit about what we can and what we cannot do with cognitive neuroscience when it comes to reading the mind, I have to provide you with a little bit of background, and that is, how could this ever work? How could we find patterns in the human brain that we can understand and that we can decode, such that we can make a sense of thoughts? And the reason for that is that we seem to know that things in the brain are not arranged randomly, as is in this image on the left-hand side, but instead we find more and more evidence that things like shape, color, size, etc., they have order. They are ordered in a certain way in the brain. And the goal of cognitive neuroscience is to find these ordering principles. How is information organized in the brain? And through this, we are trying to better understand how the brain works, both in the healthy brain, but also in the diseased brain. And on this slide here, I'm showing you a little animation about showing one of the major techniques that we're using also here at the University of Regensburg, called functional magnetic resonance imaging. And what this technique basically allows you to do is you can present participants with stimuli. These can be visual stimuli, these can be tactile stimuli, these can be sounds from the bar, or these can be even odorants. And at the same time, while you're delivering these stimuli, you measure in the brain which areas are co-activated at the same time when you're delivering those stimuli. And through this, you can try to figure out which brain areas seem to be involved in processing these type of stimuli. And using such techniques, we've made, in the last, say, 10, 20 years, a lot of progress in finding some organizing principles. Again, I won't show you all the details, but for example, we know that there are areas that care about color. We know that there are areas that care about real-world size. So there seems to be an orderly arrangement of small versus large objects. We know that there's an arrangement according to whether or not objects are animate. And the focus of today's talk, on the right-hand side, we know that there are certain areas that care about the processing of certain object categories. So if, for example, specialized areas that preferentially process faces, specialized areas that preferentially process houses, for example, to name just the most prominent ones. And this organizing principle is something that we can use when it comes to trying to read people's thoughts. So to give you an example, imagine I'm showing participants images of houses. Now here, for the sake of the argument, I've selected an image of the dome just to relate it to Regensburg. And while you're doing that, you're measuring brain activity patterns from humans using functional magnetic resonance imaging, using the technique I just presented on the previous slide. And in a very simplified version, jumping over several months of lectures, we are measuring a brain activity pattern, right? Doesn't matter, you don't need to understand more, just understand it's a pattern, right? Where white might indicate stronger activity and gray might indicate weaker activity. Now, we do that not only for houses, for which we know that there are specialized regions, we also do that for other stimulus categories. For example, faces. This happens to be the face of the president of the University of Regensburg, Professor Hebel. And you see, just by eyeballing, that the pattern that we can measure in the same region, by the way, when we present Professor Hebel's face, is different from the pattern that we measure when we present an image of the dome. That's good. We can distinguish between Professor Hebel's face and the face of the dome. And it's even further distinct from the pattern that is triggered if you show a piece of furniture, for example, like a chair. So these three different stimuli trigger very, very different activity patterns. And we can now train a classifier to distinguish, to learn these patterns such that if we have enough training data, we can present the classifier with a fresh set of data that the classifier has never seen before. And we can ask the classifier, to which of these learned patterns does this best belong to? To which one is it most similar? So here's a pattern. We are asking the classifier, what do you think it is? And the classifier magically indicates this, I think, is a face. And now we can, well, turn around the card and ask, what did we really show? And it's an image of Jan Kleine that you've just seen before. So in this case, we would say, yes, the classifier did the right decision because it assigned the pattern of a face to another pattern of a face. Okay, so this is pattern classification in a nutshell. And this is a key technique that is being used in cognitive neuroscience, both for basic research, but also for applied research. And the question is, how do we get from here to reading thoughts? Well, it's very simple. We do exactly the same. Instead of showing images of houses or faces or furniture, we ask participants, imagine a house, imagine a face, or imagine a chair, and then we measure these brain activation patterns. And there are many studies that have done that, and the interesting thing is the activation patterns you can measure when participants imagine faces or houses or furniture are very, very similar to those that you measure when you really show an image of these stimuli. So this gives us a foot into the door of reading thoughts because we can now use these patterns. And you can again compare these patterns and figure out if you ask a participant now you decide. It's up to you to either imagine a face or a house or a piece of furniture. I can now classify which of these three conditions you have thought about. Okay, that's nice. That's a very important step. So how far did we get using this technique so far? This is what I show on the next slide. So it has been demonstrated that using this technique, you can distinguish between participants imagining faces or houses. Okay, that's maybe, well, that's interesting, but maybe not so strong. We can also distinguish between participants thinking of different types of the same object. So, for example, phase 1 versus phase 2, Professor Hebel versus Jan Kleine. We can also distinguish between movements that a participant is about to perform. So imagine, instead of asking participants to imagine visual stimuli, you can ask them, please plan a movement such as reaching for an object or lifting an object or turning an object around. And you're measuring these brain activity patterns during the planning phase before they are executing the movement. And you're training a classifier to distinguish between these different patterns, and you try to predict what is the upcoming movement. And again, you can distinguish based on these activity patterns between different types of simple movements before the movement is actually executed. Okay, so again, an important step. So far I've shown you that we can distinguish between different imagined stimuli or between different imagined actions. But can we go further? Can we actually also visualize what someone has thought about? And for that, I want to go one step back. I want to show you an example video. I spare you the technical details, but I think it's making an interesting point. Here, researchers tried to reconstruct human brain activity while they watched very complex naturalistic video stimuli. And what you will see on the left-hand side is the clips that they actually saw. And on the right-hand side, you will see the reconstructed clips from brain activity that were tried to be predicted by an algorithm that has learned to associate the patterns of brain activity that were measured in the training phase. Okay, so trying to predict brain activity and by that reconstructing what the participant has seen. Okay, so I play the movie. There we go. And so the way this works is you basically show a lot of different videos and you're using a deep neural network where the network learns to associate the features that are present in the movie, and it tries to associate those features with activation in each different part of the brain. And once the classifier has learned these associations, you're now trying to predict using new movie stimuli which of these movie stimuli can best predict measured brain activity, and then you're averaging together those movies with the highest prediction accuracy. And this is how you generate those overlays. Now the question is, okay, this is for stimuli that participants have seen. How well does this work if participants only imagine those stimuli? And this is what we will see on the next slide. So I show the video again. So on the left side, you see what the participants were instructed to imagine. So simple shapes, for example, or also some naturalistic stimuli. And on the right-hand side, you see what the algorithm tried to reconstruct from this brain activity based on the technique that I just highlighted. I play it again. So the take home here is it's getting there, but it's not perfect yet, right? So, and it's certainly not as precise as the video I showed on the previous slide where the movie was reconstructed using real visual stimulation. Okay, so the field is rapidly progressing. So how can we use such techniques? Here are some example applications. So these techniques are more and more used for neurofeedback, for example, for the treatment of pain, depression or anxiety, where you measure activation and you give feedback based on activation patterns that participants have been trained to produce. If you ask participants to imagine certain movements, it's easy to see how this relates to training to use artificial limbs and prostheses. We can also use such techniques, and it is being used for communication, for example, for those that for some reasons cannot properly communicate with the outside world anymore. And interestingly, you can also use it for diagnostics. For example, if you wish to distinguish if someone that has been diagnosed with a vegetative state still shows signs of consciousness. And this brings me to the last point I want to present for today. So this is a case of a 23-year-old patient that had a severe car accident and suffered from traumatic brain injuries, and the diagnosis was that she was suffering from a vegetative state. So from the outside world, it was not clear whether this patient was actively processing anything because she could not produce any signs of being aware of what was happening around her. So what the researchers did is they asked, first of all, a group of control participants to perform different types of complex activities, either imagining to play tennis, and we've just learned that imagining things produces distinct activity patterns. So on the left-hand side here, you see activity patterns when participants imagine playing tennis. And in control participants, this is very distinct from the activity patterns that you measure if participants perform spatial navigation. So for example, going from your kitchen to your bathroom, okay? And now they gave the same instruction to the patient that had been diagnosed with vegetative state, from which they were quite certain that she would not understand because she could not answer. But the activity pattern that you found in this patient was very, very similar to the healthy controls. And they then moved on and used this technique to ask 10 questions to this patient that only the patient would know, that were very specific to her own biography, that she had to answer with yes or no, using tennis, telling tennis for yes, and using spatial navigation for no. And she answered 9 of these correctly. The 10s she couldn't answer because she fell asleep. So this is just to indicate this is a very powerful technique, and since then this has been replicated in quite a few patients. Okay, so coming to the very beginning of my talk, mind reading, future of fiction, I hope I convinced you that yes, actually there's quite a lot we can already do. There's also still quite a lot we still need to learn better. But certainly an important precondition, if I want to read your mind, I wouldn't be able to do it here in the Degginger, because I would have to convince you to either jump into the MRI scanner, or I would have to ask you to wear an EEG helmet. This is at least what's the state of the art. And with this, I'm coming to my final slide. If you would like to find out more, here's a QR code to my research group, the chair of Cognitive Neuroscience at the university. You're more than welcome to get in touch if you have further questions, also afterwards over a drink. And by the way, if any of this interests you and you want to find out more, we have this fantastic new master in psychological science where we learn these and related techniques, and we happen to have one of our master students, Jonas, who's somewhere here. There he is. So if you want to ask more about this wonderful master program, you can also ask Jonas, and here's the QR code, and I'm happy to take questions.